Hello students, welcome to today's lesson where we will be understanding function notation and the vocabulary needed to solve various problems. In our previous lessons, we discussed basic terms such as input, what we put into the function, and output, what we get out after applying the function. The plan for today's lesson is as follows. We will introduce the term operation, which describes the specific process the function performs on the input to generate the output. We'll start using the notation fx instead of y. So fx equals x squared plus 2 emphasizes that x is our input. We'll then look at functions that can be combined or composed, meaning the output of one function can serve as the input for another. Finally, we will understand the importance of order in composite functions. Let's delve into the main concepts of today's lesson. In our previous lessons, we discussed basic terms such as input and output. Today, we will introduce the term operation. The operation describes the specific process the function performs on the input to generate the output. For example, consider the function y equals x squared plus 2. Here, x is the input, and the operation involves squaring x and then adding 2. To make our notation clearer, we will start using fx instead of y. So fx equals x squared plus 2 emphasizes that x is our input. Functions can be combined or composed, meaning the output of one function can serve as the input for another. Let's take two functions, fx equals x plus 1 and gx equals x squared. We can form a composite function gfx, which means we use the output of fx as the input for gx. Writing this out, gfx equals x plus 1 squared. Notice how the expression inside the bracket, x plus 1, is now our new input for g. The order in which we combine functions matters. Let's revisit the functions we just discussed. If we first apply fx and then gx, we get gfx equals x plus 1 squared. If we reverse the order and first apply gx and then fx, we get fgfgx equals x squared plus 1. Notice how gfx and fgx yield different expressions. This difference highlights the importance of order when dealing with composite functions. Let's work through a quick example to solidify our understanding. First, define two functions. Here we have hx equals 2x and kx equals x minus 3. Let's find hkx and khx. First, we calculate hkx. Kx equals x minus 3. Therefore, hkx equals hx minus 3, which equals 2x minus 3. This makes 2x minus 6. Next, we calculate khx. hx equals 2x. Therefore, khx equals k2x, which equals 2x minus 3. Again, we see that hkx equals 2x minus 6 and khx equals 2x minus 3 are different, emphasizing the importance of the order of operations in composite functions. In summary, understanding the concepts of input, output, and operations in functions is crucial. Combining functions allows us to create composite functions, but we must be mindful of the order in which we combine them, as it affects the result. Keep practicing these ideas and you'll feel much more confident. Let's consider some more complex functions. Define these two functions. Px equals x squared and qx equals 2x plus 5. First, let's find pqx. Begin with qx. Now use this as the input for px. Simplify this. We are left with pqx equals 4x squared plus 20x plus 25. Next, let's find qpx. Begin with px. Now use this as the input for qpx. So, qpx equals 2x squared plus 5. pqx and qpx give different results, highlighting the importance of the order. Now let's work on a more challenging problem. Define two functions, r is equals x cubed and sx equals x minus 2. First, let's find rsx. Begin with sx. Now use this as the input for rx. To simplify x minus 2 cubed, we multiply out the brackets as follows. So rsx equals x cubed minus 6x squared plus 12x minus 8. Next, let's find srx. Begin with rx. Now use this as the input for Sx. So SRx equals x cubed minus 2. In today's lesson, we introduced the term operation, which describes the specific process a function performs on the input to generate the output. For instance, in the function fx equals x squared plus 2, x is the input, and the operation involves squaring x and then adding 2. We also explored composite functions, where the output of one function serves as the input for another. Using the functions fx equals x plus 1 and gx equals x squared, we learned how to form a composite function like gfx, resulting in x plus 1 squared. We noted that the order in which functions are combined matters, as gfx and fgx yield different results. In summary, understanding input, output, and operations in functions is essential. Combining functions to create composite functions requires careful attention to the order of operations, as it significantly impacts the results. Watch the rest of the GCSE Maths course at Sophos Education.